start. So my name is Christian, and I'm a postdoc here at ITC, and it is my pleasure to introduce you to Dr. Cumrun Vafa, who is visiting us from here, from the main campus. So he's the chair of the physics department, and he's appointed as Tinken University professor. I think it was a couple of weeks ago, maybe, where you got this. You were one of the 4 professors in Harvard to get this highest distinction. So, well, most of you might know Cumrun, but then he basically did his PhD in Princeton University under the advice of Edward Witten. So as you can guess now, he's an expert of string theory and also connections with quantum gravity and other aspects of mathematical physics. So then today, I presume he's going to talk to us about string theory and its connection to the dark sector. So all yours, Cumrun.
Thank you. Thanks, Christian. Thanks so much for inviting me to give a talk here, which is a great pleasure because I think a lot of exciting thing is happening in cosmology these days. And I think the connection with fundamental physics and cosmology could be a beautiful connection in the years that's unfolding right now. So here, I want to describe some of the work that we have done in this direction. And so there are 2 ways I can orient my talk, and I have decided the way I will show you. But one way is just say, forget about motivation from string theory. These are the justice-self equations motivated from string theory, which would be relevant for cosmology. This is not what I'm going to do now, even though that would have been a short summary. So I could have summarized the whole talk with 1 slide, saying this is the model, and this is, but you wouldn't see why or how and so on. So instead of doing that, I'm giving you some long song and dance explaining how we are coming to that kind of picture, okay? Otherwise, the model is extremely simple. Ultimately, I will show you. So the basic idea is that quantum gravity is very restrictive. And if you just start with a set of consistent quantum field theories and just say, oh, I just put metric on it and couple it to gravity, it just doesn't work. Even though classically you can write down the equations, no problem with the action. The action principle makes perfect sense classically, but quantum mechanically it does not make sense. This is surprising because the usual Wilsonian perspective of effective field theory suggests that it should have been okay. You just take a theory with a Lagrangian, some symmetries. It should be something which gives you that. But gravity is very different, and that's the main point. And that's actually a good thing, because precisely because of that is that we can make predictions about quantum gravity. In other words, quantum gravity tells you not just good old any theory write down with metric is okay, which has been the way people have operated both in particle physics and cosmology, just writing down models, just adding this or that to go beyond the various standard models of cosmology or particle physics. Gravity, adding quantum gravity in the mix completely changes the story, and that's the main message that's missing that we have learned in string theory. So this is the main point I want to mention. And what is it that has changed in the connection with cosmology is my main emphasis today. So naive naturalness ideas fail, and there are only a finite number of these theories which are consistent with quantum gravity. That's already very surprising. So I'll just give you one example. So if you take, for example, n equals to 4 Yang-Mills in 4 dimensions, if you choose any gauge group, it's perfectly fine quantum field theory. But if you couple it to gravity, any group higher than SU23 doesn't work. Only up to SU23 work. SU24 doesn't work, 25, etc. None of them work. So you have a finite list. Suddenly, out of infinitely many groups which are okay, adding gravity tells you, no, you have a finite list now. So that's an amazing reduction to a finite set from an infinite otherwise set. So here I want to use these in the context of string theory and tell you what it will imply. So the small parameters, so let me just see, is this the constant theory formula? So is this the talk for the lunch or did you put the right one? I just want to make sure this is the, no, you didn't. The other one. This is the other one, I thought so.
Some spoilers. But they still come to the lunch,
It is a similar. There in the lunch talk, I'm going to give you a summary rather than the full thing. So this is based on a talk that I've given with a number of papers with a lot of people here. But the main one I'm going to talk about is this last one, which just appeared in July this year. So I already told you about this. So the Swampland program is to find out what are the restrictions. How do you get these restrictions, and what qualifies as a good theory? So aim of this talk is to combine these criteria with the smallness of dark energy. So the dark energy, or cosmological constant, in fundamental unit of physics is extremely small, something like 10 to the minus 122 is an extremely small number. And it turns out that when you have small parameters in string theory coupled to gravity, it means something extra, not just that one parameter is small. Small parameters do not arise just randomly. They always have some extra pieces attached to them. And that's the piece I want to tell you about. And it turns out that when the energy is positive, also there's another attachment, which seems to be that it's not possible to fully stabilize the system. That having just positive energy always wants to go down. And the only question is the time scale and how it's going to go down. We have found no stable examples in string theory with positive energy. Negative energy, no problem. Positive energy, no examples. So we have an instability with positive energy. That's one feature. And the fact that it is small. These are the two features that's going to play a prominent role for what I'm going to tell you. So part of the program that tells us that if you have some right. So there's this duality and distance conjecture, which tells you what happens if the value of lambda is so small. Just the very smallness of the value of the dark energy implies an existence of an extra dimension, which is not so small, namely it's of micron scale, fifth dimension. And it turns out that this allows you to unify the dark sector, because just the smallness of lambda leads to the dark matter candidate automatically being the gravity waves in this extra dimension, what we call the Kaluza-Klein gravitational modes in the fifth dimension. And the instability of this lambda basically connects the Swampland de Sitter conjecture, or TCC conjecture, Transplanckian censorship conjecture, which connects to the instability of when you have positive dark energy. So these are the two important features. And these two features lead to cosmological consequences, that dark energy density and dark matter mass vary in correlated way. That dark energy and dark matter cannot be stable, and they should vary. So this is a particular consequence of these two. So let me first tell you about what is this distance conjecture. So distance conjecture means just simply the following statement, that if you view your field space, now what do I mean by field space? Let's say you have some scalar field theory, and you can choose expectation values for it. And the expectation values for a field is parameterized by some space. I'm calling here the M. So this is the parameterization of your field space. And suppose you go large values in value of the expectation value of a field. The claim is that if you ever do that, there always will be tower of light states appearing when you go to large distances in expectation value of the field phi. So you get a tower of infinite number of particles whose mass scale, the mass scale of the tower, goes exponentially down with larger and larger phi. This is totally unexpected from field theory. Why? Why should it be that if you go in large distance in field space, like if you have a free scalar theory, just take a free scalar theory in 4 dimension, you would think nothing is exotic, take any value of it you want for phi equal to 0, phi equals to whatever scale you want to put. The statement here I'm making is that if that scale goes larger and larger compared to M Planck, you will inevitably get infinitely many light particles whose mass scales with exponential, goes down with the exponential of phi in distance. Remarkable. How do we know this? Well, this is precisely the feature of string theory, which is what we call as duality. Duality symmetries means when you go to these extreme values, like small parameters, large couplings, small couplings, you get a dual description. What is a dual description? Dual description just means that there are other degrees of freedom you had ignored, which become light. That's precisely these towers. So these towers are precisely the degrees of freedom that make up the different description of the theory in these extreme parameters. So that's the duality here. So the distance or duality conjecture says that this is not just true for string theory, it's true for any quantum theory of gravity. That is, anytime you have a large parameter in your theory, you are going to get a dual description. It's not going to be the same description. The description you started with breaks down because of the appearance of these light degrees of freedom. So we have a huge amount of evidence for this, and every example in string theory has this property. A deep proof of why this should be true from quantum gravity we don't have. So I cannot prove to you that this has to be the case for quantum gravity, but we have a lot of evidence from string theory that this is the case. There are some heuristic arguments, even without using string theory, why this may be true, but I wouldn't call it a proof. So I would say it's a strong evidence we have from string theory, and some heuristic arguments without using string theory for this conjecture. I'm going to assume that statement. Now, assuming this, we know even one more statement. It's actually more specific about what this light tower is. I didn't tell you what is this light tower. This light tower turns out to be only in two possible ways. It's either some extra dimensions are becoming large, and these are gravity waves in the extra dimension that becoming light. So the scale goes like 1 over r. So the mass goes like the 1 over r, which is just the KK mode, the usual harmonics of the graviton in the extra dimensions. Or another way this could happen is that this parameter phi could be labeling for you the string coupling constant, and it's getting smaller and smaller. If that happens, instead of this tower being the graviton waves, you get a tower of light string states. So either it's a light string states, which we have in string theory, like towers of different strings, which are light, or this tower of gravitons. And this is called the string emergence proposal, that this is the only two possibilities. That's what we have seen in string theory, and I'm going to assume that. So in the context of de Sitter or ADS, it doesn't matter which sign you pick for lambda, this picture suggests that lambda itself is like the expectation value of some field, and the fact that there should be a tower because this lambda is small implies that there should be some tower of light particles whose scales like lambda to the alpha. And you can put a bound on alpha to be between 1/2 and 1 over d. The upper bound comes from the Higuchi bound, which is the unitarity bound in de Sitter space. And 1 over d comes from just simply the one-loop vacuum energy contributions for this tower of mass light particles. If you put these together, you find the only option for this to be not inconsistent with observation. There's only one possibility, that there's only one of the extra dimensions, not any other, just one of the extra dimensions, what we call the dark dimension, the fifth dimension, is something in the range of 0.1 to 10 micron. This is basically lambda to the -1/4 in Planck units. So if you take the dark energy, just raise it to its energy per unit volume. So if you want to get a length scale out of it, it's lambda to the -1/4. This gives you something in this range. Yes?
Wasn't there a limit from the Seattle experiment on the fifth dimension, on the extra dimension of order a millimeter? Or where is the current experimental limit?
Oh, I'll come to it. Maybe I will say it is 30 microns the current bound.
30 microns.
30
so
microns.
It's a factor of 3.
Factor of 3 up to, depends on what, this is the range. We don't have a precise number. Because there are order 1 numbers here, I don't know how to compute. So this is the range, and now people are doing experiments to measure, to see if there's any deviation to 1 over r squared force law up to 10 microns. So that's within a year or two, we should have some results for at least 10 microns. So that's reassuring that it's close to the range we're talking about.
So why does it have to be extra dimension, but not other light states?
Why should there be what? Extra dimension?
So why this...
why this tower?
Has to come from...
Yeah. So this is what I was just saying here. So in other words, in string theory, this tower is not any tower. It's not just, when I said it breaks down, it only breaks down in 2 particular ways. It's not just some tower. It's a specific tower. It's either a tower of light states having to do with the one space becoming, or 1, 2, or higher dimensions opening up, or the string coupling getting to be 0, in which case the tower of string states become light. And so it's either this or that. You can show that it cannot be string tower, because if it was string tower, you would have already expected that you will have a gravity which is strong at the scale of electron volts, which is not the case because we know LHC and so on don't even see black holes. So that's not possible. The only options is extra dimension. And if you want to do 1, 2, 3, 4, how many dimensions are getting big, you find that if it's more than 2 or higher dimensions, you get the Planck scale to be too low. Again, it would be violating experiment. The only option is 1 extra dimension with this size. So you're completely nailed down just from this simple argument. So it's nothing really remarkable. So we are not constructing a particular stringy model. We're just using the general principles we think are true without actually telling you more detail about which example in string theory realized it. And that's in fact good because we don't want to, if I use, oh, consider this example, you would say, oh, why not the other example? Why not this one? So the main point is not to use examples, but to see whether the principles force you. Here I'm telling you the principles will force you.
So the mass is low, and you said it has to be a large phi. But in, for example, some other string theory constructions like Bosso-Martinsky, they have a lot of states.
Yeah. So let me say this more precisely. Usually the lambda in the, for example, string constructions are given by fluxes.
Yeah.
So discrete parameters. Here I'm parameterizing those discrete parameters with the parameter phi. So it is quantized. I'm just mimicking it like that. But in string theory, typically there are fluxes. So the way we think about it is that if this is the fifth dimension, this extra dimension, and this is the micron scale, let's say, our universe cannot be living on this one. In other words, electrons, quarks, etc. cannot propagate in the fifth dimension. Because if it did, we'll get a tower of electrons, not just the zero mode of electron, but we get a different wave, the different harmonics of the electron, and which will separate in mass by milli-electron volts to electron volts. So you have a huge tower of electrons, huge tower of quarks. That's not the case. So our universe better be localized in the 3 plus 1 dimensional subspace of this 4 plus 1 dimensional universe. So we have no other choice but to say we are localized, our universe is localized like this. But what is exciting is that it automatically leads to a unification of the dark sector. In other words, I was saying that the smallness of lambda implies that there are this tower of light states. And this tower of light states, which is graviton in the extra dimension, can naturally play the role of dark matter. So I don't have to put a candidate for dark matter. It's forced on me. Just because there's extra dimension, there's a light tower of particles, and that is a natural candidate for dark matter, which would be gravitationally coupled only. So it's weakly interacting automatically without my putting it by hand, and it's hard to detect, as the dark matter is. Fits all the bill we know, and it's predicted by smallness of dark energy. So dark energy and dark matter in this sense become combined. It is called dark matter because it's just a KK mode. Now, it's not, the word cold here depends on what you mean by the word cold. These are not in thermal. These are not in thermal equilibrium, so that's the first statement. So there's no temperature. But if by cold you mean they don't have velocity, it just depends on their masses.
Right.
So it depends on how what's their masses, and I can tell you what their masses. I think in the next one I'll tell you or not. Yeah, here. So the way they would get generated is that at some point, our universe, at least will have to have. We know that the Big Bang nucleosynthesis took place, which means at least the universe at some point was temperature MeV or so. We don't know what's a higher temperature it had to be, but it turns out that if you allow the temperature to go up to GeV scale, so suppose our universe here I'm drawing it by this hot red kind of region, where our universe is at thermal equilibrium of GeV temperature, it will automatically couple to gravitons. Why? Well, because gravity couples to everything. In fifth dimension, there's graviton, also is in fourth dimension. So the gravity in fifth dimension couples to the energy momentum tensor on the 3 plus 1 dimensional subspace, which is our universe. So if you have a hot part of the universe, the gravity couples to it using Einstein's theory universally, so we don't have a choice. And so that fact automatically generates gravity waves here. Now, at the time of GeV scale, which is the radiation-dominated era of our universe, this would be very infinitesimal, like the tiny piece of the matter that's generated. But as the universe cools off fast with the radiation period, these become the dominant feature and stay to be the dark matter candidates, these guys. So these guys, which are started at the GeV scale, that means their masses. So I told you that this tower scale is milli-electron volt to electron volt. That's the scale. So you're creating way up here at 10 to the 9, 10 to the 10 level of these guys. So you populate, it's not just one dark matter, you populate a large number of them, but they are in different mass ranges, generally around that range. And then as the universe cools off, they become the dominant dark matter candidate. So they typically go down in mass, but they don't lose total mass. In other words, it's approximate conservation of mass, namely a level n goes to n1 plus n2. You decay a graviton couples to two different ones, n1 and n2, and their masses almost add up. But in other words, the average mass goes down without the total mass going down. Yes?
So are these extra dimensions also present during inflation? Like
we don't want to speculate we want to be as close as possible to observation. We don't want to speculate anything before. How did you even get to this temperature GeV? So I'm not going to even assume we did have inflation. So in fact, there are different ideas people have in whether there was an inflation or not. So, but that's not relevant for my talk. So I would rather not get there. If you wanted inflation, one way would have been you want an inflation to end up on the to decay to the modes in our universe of this temperature of GeV. Initial, you could call initial temperature in the inflation language, but I'd rather not speculate about that. So I just want to say we start GeV, and if you roll down the units from there on, you get the right amount of dark matter produced. Now you could say why initial temperature GeV, and then there is an argument from string theory why it's natural to do GeV. It turns out to be related to the cosmological constant to the 1/6 power. And I can explain why maybe after the talk if you're interested, but the main point I'm trying to make is that this GeV is not random either. So there's a connection again to dark energy and somehow relates to this, I don't know if you have heard about the Dirac's large number pattern. Like why are these patterns? One of the patterns that he had noticed is that the masses of a proton and so on, or masses of the pions and so on, is related to the area of the universe by the -1/6 power relation. And that actually is the explanation that I'm saying one can give a heuristic argument why. So the GeV scale is related to the statement that the universe has to have settled down to a 3+1 dimensional geometry. Otherwise, if the temperature was higher, it would have given the vibrational modes of the extra dimension, it would not be stable. So you cannot go any higher temperature. So that sounds like at least a motivation for that. But let me not bother with that. Now, when I said these energies decay down, they almost conserve energy. That means that mode number n goes to n1 and n2, where n1 plus n2 is approximately n. But they are not exactly equal. So you lose a little bit of dark matter, very little. So it's not going to affect. It's not going to be a big issue for the bounds that we have. But actually, it might have an imprint because some of the energy is converted to kick velocity as the dark matter decays. And this would be actually some model we are actually studying now, whether or not this would be relevant for issues like core cost problem in the galaxies, in the core cost problem that we have for dark matter. That could potentially explain that issue, but we don't know. But the kick velocity is something naturally comes out in kilometers per second range, or 10, 20, whatever the range is. It's around that range. So we are studying whether that's a useful model for that. That's not what I'm going to talk about here. So let me just basically say the picture we have is extremely simple. Our universe is a 3+1 dimensional slice in a 4+1 dimensional universe, where this extra dimension is of the order of a micron, and initial temperature GeV, and it produces dark matter in the form of KK gravitons. And if you do, as Avi was asking about the gravitational attraction force laws, at a scale less than a micron, the 1 over r squared force law should become 1 over r cubed. So therefore, that's an experiment people are doing right now in two different groups, one in Austria and one in the US. They're trying to actually measure whether there's such a deviation. So this is the first part I wanted to tell you. That is, smallness of the dark energy, just the smallness, nothing else, is already motivating you a candidate for dark matter, some large dimensions, and that already is an amusing statement because it gives you a natural candidate for why dark matter is weakly coupled. Direct detection of dark matter would be out of the question in this picture because they're just gravitational. The only effect you will see is gravity. And that's getting more and more consistent with observations. It's all these direct detection attempts that's coming back empty-handed. So these are all predictive statements that we are making. But there's another feature, is that dark energy seems not to be possible to be stabilized when it's positive. So this idea that you have this minimum of a potential whose value is the dark energy, which is this, this model that we kind of usually draw when we talk about what dark energy could be, cosmological constant being a minimum energy value for some field space, is a good story, but actually is not realized that is in string theory. So what happens is that we see that, for example, if you go in large field space, you always find the potential decays down to 0. For example, you can show it cannot be constant like this. It just goes down to 0. It goes down to 0 with a coefficient which is 1 in Planck units. So in other words, if you compute v prime over v, where v is the potential as a function of phi, you get order 1 numbers times m Planck. Why? Well, this happens in all string theory examples we know. It cannot be something like a constant. It always goes down exponentially. So, and also, so we know that for large values of the field space, the potential is not stable. It goes down exponentially down, and m prime also goes down exponentially with some other coefficients. The masses, I told you the tower goes down, and this also goes down. The value of C we actually know, the bound. In 4 dimension is square root of 2 in Planck units. So it's not just some random more than one number. It's root 2, square root of 2. In fact, square root of 2 is precisely the bound which tells you that you cannot have inflation asymptotically in phi. So it's too steep for it to be inflationary. If it was a bit gently sloped, you could have an inflationary situation, but if it's too steep, you cannot. The bound tells you in string theory, all the examples in string theory lead to non-inflationary situation asymptotically in field space. Yes?
So you're saying the KKLT type of thing is not fully realized?
Sorry, what?
KKLT, this kind of construction is not fully realized because they have minimum.
KKLT attempts to get minimum. That's a scenario that people have tried in string theory. There are many issues with that people are describing. So I'm not gonna assume that's the correct model. But I'm going to tell you what we actually really know. So these statements that I told you about is what we have established in string theory. The question we know, the question that people ask is what happens inside when you're far from the asymptotic regions? Asymptotic regions doesn't give you a critical point for the potential. Question is, what about the middle?
And also, when you say this exponential potential, does it have to decay? Why does it have to be decayed to 0, but not negative or positive? The overall constant.
Well, why is a good question. The main statement I'm making is that if you have a weak coupling region in theory, it automatically means that V goes to 0. That's the way it is. It could have gone from negative side to 0, in which case you would have anti-de Sitter examples, but it could also go from positive side. I'm interested in the positive side because we're interested in our universe, which has positive dark energy. So it goes to 0 positively in the case that I'm interested in, and there's a bound on the value of C that bigger than square root of 2, asymptotically bigger than 1.4 in Planck units, in reduced Planck units. Okay, and so asymptotically also the tower has the same property. The slope of this exponentially goes down, the tower also goes like this. But we don't know exactly what happens inside, which is related to people are trying to say, can you get a metastable critical point, which could play the role of a dark energy, stabilize. Well, notice that even if you could do that, it would be metastable at best, not stable. In other words, because I'm saying asymptotic is going to go to 0, so it will decay. And then you could say, well, who cares? If it's trillions of years, it's basically stable as far as I care. So people are trying to find examples like that, but there have been no concrete example which actually works that people can establish that's the case. So indeed, if you, and moreover, it tells you that there is something to be said. Why is it like this? What principle gives you such a behavior? So here we in the different papers in 2018 and 2019, we made a series of statements that we motivated by this behavior. We could say that, well, maybe this behavior, V prime is bigger than a constant times V, is true everywhere, except possibly there are some regions, maybe you get to the top of the hill potential, and you could have an instability where V double prime is negative. As long as you have a big instability, you won't have a flat region. So if V double prime over V in Planck units is sufficiently negative, or V prime is bigger than C times V, then this could be a potential feature of instability that will be persisting everywhere in this space. But I think a more motivated statement is what we call the Transplanckian censorship conjecture, which is what I will tell you, which can be more motivated from cosmological perspective. Suppose you have an expanding universe. And suppose you start with a region which is sub-Planckian. And suppose this region expands so much that overtakes the Hubble horizon. Then it will freeze out, and those are the kinds of modes that, for example, in inflation models want to be described as leading up to structure formations later, the inhomogeneities. But sub-Planckian modes means sub-regions of smaller than Planck length, which are unphysical. Okay? So you could say that bigger regions growing out of the horizon can freeze, and that's not so shocking. But if you're saying something which is smaller than the Planck scale, which is we believe not to be physical, to grow from outside the Hubble horizon and freeze, and then they become physical, sounds strange. So we just said, suppose we impose that this never happens. in any quantum theory of gravity, you cannot have a situation that these sub-Planckian modes cannot overtake the Hubble horizon entries. Let's just assume that. We don't have a proof that it has to be, but sounds reasonable potentially. If you do that, you immediately get the bound here I told you about. You prove that asymptotically V prime is always bigger than CV with the C that's measured in string theory. So it exactly explains the asymptotic behavior that we know is true. Now it will tell you that in the interior region, you could have metastable points whose lifetime is short compared to Hubble. So in other words, you can find the lifetime of our universe would have been 1 over h times log of 1 over h. No more than that. So in other words, you would have almost, you couldn't call it de Sitter anymore because the lifetime is of the same scale as the Hubble itself. So therefore, in some sense, it's unstable even there. But generally speaking, it will give you bounds which are moreover consistent with this kind of picture with the order 1 parameters. So let me then tell you what these lead to. So this C and C prime should be viewed as logarithmic derivative of the potential and the mass of the dark matter scale. Asymptotically, as I told you, the C is bigger than square root of 2. That's this one. And C prime turns out to be bigger than 0.7 asymptotically in field space. In the interior, we don't know what these bounds would be. In particular, they can go all the way to 0 because you could have a hilltop potential, like V prime could approach 0 at the hilltop, for example. But one thing we can show is that the interior, if you assume the Transplanckian censorship conjecture I told you about, the average value of the slope, the logarithmic slope, is always bigger on the average than this number, which in 4 dimensions is 0.82. So the slope of the potential on the average is expected to be bigger than 0.82 in 4 dimensions from this principle. Moreover, note that if C prime is not 0, since phi is essentially massless, it leads to a fifth force acting on the dark sector, because the dark sector mass is a function of phi, but phi is essentially massless. If the mass couples to phi, if the dark matter mass couples to phi field and phi is massless, the exchange of this massless mode creates an attractive force on the dark matter whose scale is proportional to twice C prime squared compared to gravity. There is a bound on that in the dark fifth force by Kamierkowski et al. Using the Sagittarius tidal disruptions that could have been there. Lack of observation leads to a bound that the C prime, the parameter I'm telling you about, observationally cannot be any more than 0.2. So we have this bound from observations. We have this bound from theory on the average that should be bigger than of the order of 0.82. But what does this field represent? It's the size of the extra dimension. So I'm going to come back to the first thing I was telling you about. This phi I'm telling you about is naturally connected to something having to do with the extra dimension. So therefore, you can think of phi parameterizing the extra dimension. And so as phi evolves, you could imagine this point is our universe, and this length elongates. So it doesn't have to affect the standard model degrees of freedom because they could be just stay put. So it doesn't affect the mass of the electrons or protons or the fine structure constant. All of those will not change because they are localized. But the things which are not localized will change potentially. So in particular, the mass of the dark matter will change just simply because it's the KK wave. So it's just the redshifting phenomena. That is, if you just expand the extra dimension, the wavelength will elongate. The usual good old redshifting will decrease the mass of dark matter simply by that, or if it's contracting, will increase it, depending on which way you're going. The change of this direction will affect the dark matter. So if the point here is that if this extra dimension is not stabilized, it will affect both the dark energy and dark matter in a correlated way. So it was based on these models that in 2019, we wrote this paper with Agarwal and Obeid, which we call the fading dark matter, where we discussed what kind of cosmology this gives rise to. Namely, the model we took was extremely simple. We said, well, we don't know exactly what's the shape of the V. We don't know exactly what's this mass. But it's natural to think that dark matter is this tower. And there is some potential, which we don't know exactly how to compute. But if the cosmology is sensitive to only a small region in field space, we could parameterize it by a local derivative, logarithmic derivative, v prime over v, and m prime over m at the point of expansion. So it's linear approximation, if you wish, near some particular value of phi. So basically, we took a simple model where you took v to be exponential in phi because of small variation. It's the same thing as saying you take v to be exponential, and m to be also exponential with parameters given by c and c prime. Is that clear? So we get an extremely simple model.
Kind of related to things that
Yes.
we are more familiar with.
Yes.
At the level of an equation of state.
Yes.
What is this?
I'm coming
You're
to
going
it.
to tell
I'm
me.
coming to it. That's where I could have started my talk with
Okay.
exactly just that, which is just a one-liner, basically.
Okay.
One other thing, you,
Yes.
you mentioned the GeV as an important energy scale in your theory.
Yes.
But then today it's milli-electron volt. Why do we see these changes today? Why wasn't the...
Sorry. Mid-electron was also back then. I said the states that are occupied in this mid-electron volt region was 10 to the 9 and 10 in the tower.
Yeah, but why now? Why do you get the changes in dark energy now?
No, I will tell you when you will see it. I'm coming to that. The dark energies change extremely small amount. I will tell you what is this. So that's not going to affect too much. The story is not, even though I'm talking about evolving, it's not such a big difference. So
It's slow.
it is extremely slow. It's extremely slow. It cannot be anything other than that. Otherwise, the cosmology would completely be violated with what we already know. And moreover, the fact that C and C prime order 1 doesn't make it go too fast either. In other words, these ideas from string theory are consistent with the fact that we could have been fooled to think that the dark energy is constant. Why? I'm telling you V prime is of order V, but V is 10 to the minus 120 in fundamental units. So I'm telling you V prime is 10 to the minus 120. So it would be easy to confuse that as 0. In other words, the fact that up to now the dark energy was not measured as moving is not surprising. We were expecting it not to be easily measured because V prime is of order V and V is 10 to the minus 122. So we had a prior that it would not be catched easily, which is why we wrote that paper in 2019 saying, oh, don't be so sure that the dark energy is not changing just because you didn't see it yet, because it's supposed to be very small changing. So we had a theoretical prediction that it should very slowly change potentially. That's the reason we wrote that paper. 2019, no evidence for any change in dark energy or dark matter existed back in 2019. So, but nevertheless, that's the paper we wrote. Now, so you can have two possibilities. So if you think about the potential V of phi for this, think about phi as the extra dimension radius. So the mass as a function of phi, if the radius becomes bigger, goes down, like, let's say like this, like 1 over r. And so that's this purple curve. But the potential, we don't know how it looks like. We know asymptotically it's going to have some exponential behavior. Maybe it reaches some peak. Maybe it goes down. Maybe it has metastable. We don't know exactly what is this black potential. And moreover, we don't know where we are actually starting the universe. We could have been here. We could have been here. We could have been here. So basically what we would be doing, wherever you start the phi, you can locally model this by some v prime over v or m prime over m as if it's exponential, which is what we're going to be doing. In other words, it's just a local parameterization. Of course, you should check whether the first order assumption was good enough, and we will check it, that ends up being good enough. In other words, the variation of the phi field, if it's sufficiently small, then you're okay. And that's what we're going to check. But as far as the model itself, we just think about the extremely simple model, 2 exponentials for V and M. So the dark matter mass and the dark energy are both function of another mass of scalar field phi with slopes which are given by this parameterization, where C and C prime are order 1 in Planck units. So if you want to restore M Planck, put a 1 over M Planck in this formula, and C and C prime order 1. And there are 2 possibilities, depending on whether you start on the left or on the right of this one. If you start on the left or right of them, the slopes would have opposite sign, or if you're on the right side, you have the same sign for the slopes. That's all. Is that clear? Is it? I hope that the simplicity of the model is very clear. So this is nothing kind of like, so this you could have said, oh, these are just like quintessence models, this V. Of course, this is people have talked about for many years now about the quintessence models. And you could say, well, this is just saying that the dark matter and dark energy couple. Yes, of course. So people also have talked about dark matter, dark energy couple too. So that's not exotic either. What is exotic is that I'm predicting their slope up to order 1 parameter. That's not predicted. That you don't usually write down, and that's the stringy prediction. I'm saying the C and C prime are order 1. So I'm effectively telling you up to order 1 parameter, what are the slopes, which is very surprising from an effective field theory perspective. Is that clear? Otherwise, there would be no prediction, just writing a random V of phi over M of phi. There's nothing to say. It's just.
That's what Steinhoff was doing for 20 years.
Well, they would usually don't put, I mean, some of his group did put an extra coupling to the dark matter, but even typically they just had dark energy. Dark energy does not do the job. In fact, I'm going to claim that what DESI has measured is this piece, not this piece. I think DESI has measured C prime, and I'm coming to that. So it's not so much the evolving dark energy, it's evolving dark sector within dark matter and dark energy coupled in this way, but the part that's relevant for DESI data is mostly the C prime part, not C. So in fact, it's kind of clear. So this is coming back to your question here. There's an effective phi, which is the energy density in the universe, which is 2 pieces. I mean, I'm ignoring the regular matter part, but there's the dark energy part, V of phi, and then there's the dark matter contribution, which of course, this scales like 1 over A cube piece, and this case doesn't scale with A, but that I'm not writing the A dependence piece. The point is that there is a phi dependent piece, which is adding up to these 2 pieces. In the matter-dominated era, this is bigger than that term. So you just have sum of 2 terms, and this you can ignore to first-order approximation. It's just rho. So in other words, in the matter-dominated era, you're just rolling on this potential. Of course, this gets rescaled by a factor of 1 over A cubed, but that's besides the point. The main point is that this is the part that determines the initial flow. And what does that tell you? Well, that tells you that the matter-dominated era, you're measuring C prime. In the energy-dominated era, you will be probing this piece, because dark energy is going to dominate over the dark matter, and then you will be measuring C. Well, that's where your supernovae data and so on will be more relevant. So the claim is that the supernovae data, which is being combined with DESI data in various data set combinations, is useful to get this piece. But even without this piece, you can talk about this piece, which is whether the dark matter is evolving or not. Okay, is that clear? Now, one of the behaviors that people had seen in the context of, in particular, the DESI data, was the so-called phantom behavior, which is that if you compute the effective value for W, equation of state for dark energy, P over rho, they found that it crosses the value -1 around Z 0.5 or something, which is a little bit unfortunate. Sorry?
Forbidden.
Forbidden. So that was casting a doubt about what is DESI doing with this model for the what's called CPL parameterization. But actually, it makes perfect sense in our context. So what happens is, to compute, how do you compute the rho of dark energy? Well, you take the rho of dark energy, you subtract from it the dark matter part of the full rho which is driving the expansion. But you have to have a model for whether the dark matter is scaling like 1 over A cubed or not. So in the simulations, etc., you are taking that is scaling like 1 over A cubed. And if you do that, you're going to be making a mistake because you're assuming the dark matter is not changing in mass. So you get a correction term, which is the evolution of dark matter. And this turns out to be the correct sign, the right sign, so that actually it allows you to have an effective W becoming -1, even though if you combine the dark matter and dark energy, there is no phantom behavior. It's just that you're forcing the dark energy to be like the regular dark energy and dark matter to be like a regular one and decoupled. That does not make sense. So in other words, the phantom behavior is a symptomatic fact of the connection between dark energy and dark matter, which is natural for us. And in fact, if you plot it, this is from our models. So if I will come back to our models with the DESI data and different data set combinations, you find that W effective crosses more or less very similar pictures to what DESI team shows in their papers. Crosses it around Z equals to 0.5 and it goes down. Yes?
Is there a prediction for the delta phi? Like how much is the phi change? Like so
I'm coming to it. I'm showing you that. I'm beginning to show. So I'm beginning to show you some of the results of our MC runs, which this is one of the results of the MC runs here. And here we are showing it with respect to different data set combinations. For example, this DESI, one of them is this blue one is just DESI with just the CMB things. DESI DR2 with unions is the other one, Pantheon and DESY is the other one. This is the old SY. They have modified their data recently, so this is not including the recent modification, so you may want to ignore the purple one, but look at the other ones if you wish.
You're saying that the dark matter mass changes by tens of percent.
I'll come to it. It's not tens of percent. But I will show you. Just a second. So this is for the value for C and C prime had opposite signs, it turns out, is the preferred value. So now I come to the question about how much phi changes and how much the dark matter changes. The dark matter mass changes only about, depends on the promising models which have C and C prime of opposite sign is like this. So if you start from the original Z all the way down, it begins to change over here when the matter domination starts. And then when the dark energy dominates, as you go this behavior. So it's about 3% during the matter dominated era it goes down, but it goes back up 1% during the dark energy dominated era. Now, this is the dashed line here represents the value of C and C prime being the same, which is less preferred. But if you did that, you get more variation up to 4 or 5%. So here I'm showing you the MCMC runs and their significance over lambda CDM. So W0 WA is the usual CPL parameterization. So W0 WA called dark matter is what, for example, CPL parameterization suggests, which Desitin did. And if you do different combinations, you get something like these significances over the lambda CDM. I'm ignoring, just beneath this line was the results of DES-Y5, but since they have modified the result, I don't want to include that because that's still being debated from what the actual value is. So let me just focus on these values. If you do the same things in our model, you find the significances are very comparable with CPL parameterization. As you can see, it's not too different from these values. And now you can ask, what value do we get for C and C prime? C prime is the one that I told you determines the dark matter piece, how the exponential behaves. The slope ends up being 0.05 plus or minus 0.01 for all these data sets, which is not surprising because, as I told you, the dark matter, the evolution of the dark matter portion doesn't care about recent time. It's only dominant for the early times where the matter domination takes place, not the supernovae part. And therefore, it doesn't care about whether or not you combine it with the supernovae data set or not, it's the same value. C prime is 0.05, and that's the curve you get for the C prime. Interestingly enough, I told you that there's a theoretical bound, experimental bound by Kamikowski and collaborator, where C prime is supposed to be less than 0.2. And thankfully, we are, from fitting the data, we are getting 0.05 plus or minus 0.01, which means that the force is a factor of about, goes like square of this, so it's a factor of like 16 more than the experimental bound. So 16 times weaker than the experimental bound is the fifth force that we are expecting. So it could potentially be observable in tidal effects when galaxies collide or come near each other. So this could be extremely interesting for observations if we can do more first of all, develop the theory better and look at the observations more detailed. Possibly we can measure this directly, this fifth force, this value of C prime. And the value of C, look at it, it's around 1, or an absolute value. And remember that I told you on the average, it should be bigger than 0.82. That was the TCC bound. So I told you the expected value for the range of the slope should be around 1, but I didn't tell you what, but I said the mean of it should be bigger than 0.8, and these are very much within that range. So we are getting values which we were expecting, and the range which we were expecting from theoretical arguments that was natural from string theory perspective. So this is why we are super excited that we can now predict that the fifth force to gravitational force is around 0.5% attractive force that we would hopefully be able to find it. There's another paper that appeared actually a year before in 2024 analyzing the DESI DR1 results, and they were trying to see whether, assuming there's a fifth force, they were not studying our model, but they were just saying let's assume there's a fifth force for the dark sector only, does it help? And they found that if they put a fifth force in the dark sector of the order of 0.4%, it fits better the data that Desi was getting. So that was consistent. It's consistent with what we are saying for this model, which is automatically has the fifth force included in it. So let me conclude by saying that the ideas from quantum gravity and string theory in the context of the swampland program lead to the unification of dark sector as well as concrete observational predictions. These we made, again I emphasize, we made these predictions in 2019 at a time where there was no evidence for anything evolving, and moreover we were getting a heat from our colleagues in string theory claiming that we are disproving string theory with our paper, which is, we wouldn't go that far, but at any rate, the main point is that this is so natural that we put our neck out and wrote this paper in 2019 to say this is so natural, we better find something like this. And this model, without any change, is fitting the data pretty well up to now. Of course, time will tell when we get more data what is actually going to happen, but as of now, the predictions are pretty good compared to lambda CDM and in the range of more than 3 sigma in some cases, significance over lambda CDM, so we are super excited. But I think this shows that the connection between string theory ideas and observational cosmology, which at some point sounded like a remote connection in some form, is actually might be much more productive and relevant for what's happening right now. So that's why I feel this is quite an exciting period for both fundamental physics and cosmology. So I'm expecting many exciting things to evolve in the next few years from the data. Hopefully, we'll know more within a 5 to 10 year span. Thank you.
Thank you for the amazing talk, Cumrun. We hear questions, Abhi?
So there is one additional prediction that you didn't mention that your theory must have, and that is if I generate gravitational wave, a graviton, with a wavelength smaller than a micron, it would leak into the extra dimension, right?
Yes.
So you would lose it in our real universe.
If you had a very high energy, for example, if you had the mergers which had very high...
Wait, before I get to the source,
yeah.
but it's true that a graviton would get leaked out.
Yes.
Now, when we go back in the history of the Big Bang, right, so there were tensor fluctuations, let's say produced by some process, you would predict that all of those gravitational waves produced cosmologically with a wavelength when they were produced smaller than a micron, which is a very big scale.
No. So let me explain. So people have put bounds, for example, for supernovae and so on, because as you say, they will leak when you have supernovae events.
No, I'm not talking about supernovae.
But
I'm talking about
any
generating them in the early universe.
What do you mean by early?
Before the size of the horizon was 1 micron.
Like GeV scale? Okay, so
the universe started with temperatures up to the Planck scale, right?
So no problem. Let's go back
all the gravitational waves generated until GeV
temperature. That gives you the dark matter. So it's exactly what those are.
What I'm saying is your prediction is there will be no gravitational wave background that was generated at an era before the universe was a GeV temperature.
I'm not going back to before the GeV because
You're
I don't
not going back, but
I don't know what
prediction.
happened before GeV.
So, for example, there is a whole experimental group here by Kovac trying to detect gravitational B modes. These ones were generated on wavelengths much smaller than a micron. You would predict no gravitational waves, right?
Well, when you go back that early, you have to ask whether or not the dark dimension has stabilized or our universe has been stabilized. You have to ask many more questions. Like, I assume that we are localized in a 3+1 dimensional subspace. More precisely, what that means is that there's actually size to our universe too. You have to ask, is our universe, the portion, the 3+1 dimensional portion, is that also stabilized or is that evolving in the time scale that you're talking about? So many questions like that has to be answered before we get to that.
As to what
I don't know. I don't want to go to too early universe because I don't know. But let me finish. I don't believe necessarily that picture like inflation would suggest that there are these B modes. But I think there are other models in string theory motivated which does not need inflation and in which case does not give you B modes, for example. So I won't even necessarily go there. Namely, the duality symmetries I was telling you about suggest that the early universe might be totally different from just the same way. So let me explain it better. I told you when you have extreme parameters in string theory, you always get a dual description. What is more extreme than high temperature?
Right.
Go to higher temperature, our description should break down.
Right.
Not like inflation situation where you just have one extra scalar field.
Right.
They're very different. So what I'm saying is much more natural in string theory to explain the dual description where our universe emerged from. And what that dual description is, I don't know. But it's much less natural to expect our universe to have been good
Okay.
description at the temperature, high temperature.
So what if you have a black hole with a mass less than the moon? Less than the moon, its Schwarzschild radius is less than a micron. What is your
So then,
prediction?
if it's less than a micron, it would be a 5-dimensional black hole. So the decay rate and all that would be different. So in other words, people have actually studied. So even though I told you about the dark matter candidate being gravitons, another group has tried to view primordial black hole in this model, in the dark dimension, as potential candidates for dark matter. And in that context, they precisely because the dark matter candidate has a mass less than the micron scale, and in which case they're a 5-dimensional black hole, not 4-dimensional black hole. And it gives the range, I think the range of black hole primordial was from 10 to the 14 grams to 10 to 17 grams. And they find that going to this one, 5-dimensional one, expands the range from 10 to the 13, 14 to 10 to 21.
Yes.
So it expands the range because you have extra dimension and the decay rate is different, so it puts a different bound. So people have studied that in this model.
Have any other questions?
So, one part that was not clear to
Yes.
me. So we are seeing this kind of evolution in the universe at, redshifts of a few. Daisy is telling us. Is that are we at a special time in your model, or any time in the universe we would have seen effects like this?
So
That's the part that's unclear to me.
okay, so let me explain. That's a good question. So parts of it is yes and part of it is no. I do not know why lambda is so small, if that's what your question is. But if you ask me, when dark energy, so in the cosmological epoch, the time where the dark radiation-dominated era, matter-dominated era meet, is not too far away from where the dark energy takes over. There's almost, it's almost in cosmological scales coincidence. Why are they so close? That we can explain. That is not a coincidence. So we can explain why the dark energy scale is close to where dark matter and radiation energy density are equal. That scale we can explain without any assumption about whether lambda is too small or not. So that part, so if that was your question, yes, we can explain it. But why the lambda that I said is so small, that I can't tell you. So in other words, whether lambda being small is anthropic or not, I don't have any better explanation. But whether structure formation, so in other words, the idea that Weinberg was using to try to come up with the anthropic principle was that at some point, the matter domination should have happened for the structures to form before the dark energy took over. So dark energy could not be too big, and therefore that put a bound, and that was his statement, that our existence implies structures existed, and therefore dark energy could not have been too big. We have a prediction. That was his anthropic argument. So for our model, that's not a good argument anymore, because for us it's always the case that the dark matter, dark energy are in the same scale range. So it's not a good explanation for that. But
I guess my question was slightly different.
yes,
Your W was crossing, -1.
yes.
Redshift, modest redshift. It could have happened any time. It's happening now in the universe. Is that an accident, or is that something that follows?
Well, I think it has to do with the fact that dark matter and dark energy are close to each other in
So
density.
it's really the same thing.
Yeah, it's the same thing.
happen to
Yeah. I think it's all the same thing. We are just playing with the same parameters.
Okay.
In fact, there's only one parameter. Basically, matter density, dark energy, all of now are the same. And in fact, just not related to my talk, is also the scale that Einstein wrote for his model. He wrote the dark energy he called cosmological constant was proportional to matter density. So he kind of has more or less similar kind of a. There's no other scale in this problem. So.
That was because of his ignorance.
His ignorance, but he got it right accidentally. So he had assumed the spherical geometry curvature, but if you anyhow, so it's just a funny coincidence.
Any other questions, Scott? Let me just give you the mic. I don't know if you need it.
Does this model have anything built in to develop the inhomogeneities in the dark matter that lead to structure formation, or is that all before
That's
this?
the same. In other words, this model is almost like lambda CDM. I would say that it barely differs from lambda CDM. The only difference is that dark matter evolves in the sense I said, and the piece that I said that's interesting potentially for structure formation is a slight kick velocity that the dark matter splits to two pieces. So the core of the galaxy might be depleted by this kick. And so it could be that it could lead to some interesting observable effects. Now, my colleague Cora and collaborators have have argued the existence of dark matter galaxies with no visible matter in them. And so if they can refine their measurements to the extent that they can find the density of matter in these dark galaxies, and if the core still has that problem, it means that the baryonic physics that some people are hoping might explain the core cost problem would not be the reason, in which case something like this might be the explanation. So we're hoping that that kind of question will also be studied, hopefully.
Any other question? No? You're hesitating? Okay.
Is the evolution of W that you're predicting, does it go the right direction to solve like the Hubble tension?
No. So the Hubble tension, we don't have any improvement, and if any, it makes it slightly worse, I would say. So the Hubble tension is, I don't have anything to say about the Hubble tension, unfortunately. So I don't know. I'm not. It's not my domain expertise. I just know it doesn't. We don't help with that. Sorry.
No statements. Any last question? On the same direction, did you get to vary the neutrino mass just to see like
well, naively, if you plot it, it would be similar to what you have in your paper. It peaks near zero. But you know, the width of it is allowed. So, but we didn't go to negative range. But I mean, if you allow it to be positive, it peaks near zero.
Helps it to not be hitting the prime.
Yeah, we don't have. It didn't peak away from zero for us either.
Any last question? If not, let's thank Cumrun for the great talk.
Thank you.
You're staying with us for a long time. You spoke our language. I didn't realize.